Ever since the dawn of human civilization, gravity was the fundamental force which humanity first understood. We can understand how cannonballs fly, how planets revolved around a solar system. We can even see that when we throw a ball, predictively where and when it will land, everything out of that we can predict and understand the classical nature of gravity. Yet there is a problem when it comes to reconcile gravity's behavior with quantum mechanics, with the quanta. Now, the quantum gravity is basically an attempt which we are still willing to learn and willing to explore when gravity is expressed in terms of quantum mechanics. When the Einstein general theory of relativity's basic principles would be represented in terms of quantum mechanics. That is what is called quantum gravity. In today's video, what I'm going to do is that I'm going to give you a complete idea what is quantum gravity, how it evolved, what is the need of quantum gravity, and what are the current theories which we are still pursuing, and hopefully in near future we will unify gravity and quantum mechanics. I will be keeping apart the complex mathematics, because if I go back to the mathematics of reconciling quantum mechanics with gravity, that will eventually demand a separate video. But in this video I will give you a complete clear idea, a journey about what is called quantum gravity. My name is Shaunak and you're watching this video on my channel Physics for Students, and I welcome you to watch this video on quantum gravity. Okay, so first let us understand what is quantum gravity. If you have watched my earlier video where I have defined the term quanta, which means some or something, it is generally used in quantum mechanics in order to denote some small or specific particles, or I can say specific energy sources which will behave according to some very specific and limited area. Mechanics is basically to define the Einstein general theory of relativity in principle of quantum mechanics. So the three forces of nature, electromagnetism, strong and weak force, has now been united, and we all know that it behaves according to quantum mechanics as well as in terms of quantum field theory, which has different branches. Now, gravity as per general relativity does not work when we try to find out in the realm of quantum mechanics. Don't worry, we will explore soon the idea why it is that. But when we are trying to unify gravity in terms of quantum mechanics, we face a problem. We face a lot of issues which is still unsolved. Now the question arises that why do we need gravity to unite in terms of quantum mechanics? So let us take an example. When we are talking of a black hole, which is one of the predictions of Einstein's field theory or Einstein's field equations. Now when a black hole ultimately shrinks down and down and down, and we are arriving at a point of singularity, right? When there is an infinite amount of curvature, infinite dense, everything is very infinite, and everything shrinks to a very small, minute, I would say infinitesimal small point. Now we know that at that point all the laws of physics breaks down, gravity, the curvature becomes infinite, and the mathematics becomes a kind of a mess. So at that particular level, when we are, everything is drawn to a very small, tiny single point, then definitely quantum fluctuations will come into effect. The perturbations will come into effect, Heisenberg's uncertainty principle and all the bizarre world of quantum mechanics will be opening the door. Why? Because at Planck scale, when the general laws of physics breaks down, it is quantum mechanics which takes over. So at that particular point, when singularity, or we are considering the Big Bang theory or something which is which is reduced to a single point, then quantum fluctuations are important, and in that case we cannot ignore quantum mechanics or quantum field theory. So far so good. So when we are trying to measure everything at a Planck scale reduced to a infinitesimal dense single point, then we are trying to unify the principles of gravity along with quantum mechanics. And herein lies, I won't say limitation, but a kind of an issue which we are still trying to resolve. We find that the general theory of relativity is not working in terms of quantum mechanics. Why it is not working, we will soon find out. So we are actually trying to unify everything at one single theory so that everything can be explained simply. As we all know that Einstein didn't write quantum mechanics, and he used the word that God does not play dice. During his later years, I would say Einstein was still trying to unify quantum mechanics and gravity, because he told that quantum mechanics is something which is not comfortable with. So herein lies a basic definition of quantum gravity on your screen. So quantum gravity, broadly construed, is a physical theory incorporating the principles of general relativity and quantum theory. So this is a point where we are trying to unify everything into one single theory. But there is a problem. The problem is that general relativity, space-time curvature, and those tensors analysis really doesn't work in the realm of quantum mechanics. So the quantum gravity is trying to quantize gravity. That means we are using gravity in a sense that at the Planck's level, even the laws of general relativity or the laws of gravity will really work out. So right on your screen, I would like to show you a basic skeletal structure. So you can see classical mechanics, which is divided into quantum mechanics and goes into special relativity. Newtonian gravity got expanded to general relativity. And electromagnetism, we have got QFT and QFT in curved space-time. When quantum field theory we are trying to express in curved space-time, that is general theory of relativity, we need another theory which is called quantum gravity. So far so good. We understood that quantum mechanics behavior is not matching with general relativity reduced at a Planck scale, and not only at Planck scale. When we are overall trying to unify all the physical theories into one, we need a new theory, that is quantum gravity. The question is that why do we need quantum gravity? Let us try to find out into much more details in the next part of the video. The Philosophiae Naturalis Principia Mathematica, which is considered, at least I consider, to be a seminal and a revolutionary work by Isaac Newton, advent and ushered a new era of classical mechanics. Now, when I use the term classical, I am not saying that calculus, momentum, inertia, no. Classical in the sense that if I throw a coin, it has got a predictability that where exactly it will land into, or if I throw a ball, if I throw a cannonball, or do anything on a finite inertial or even a non-inertial frame of reference, I can tell the behavior of the system where it goes to. So far, Newton's Principia Mathematica and the classical theory was going great. Until the advent of the great genius Albert Einstein. So the classical theory was predicting everything, and still now we can find out the behavior of a system given certain initial conditions: position, momentum, angular momentum, charge in case of electricity. So classical mechanics, predictive in nature, guiding the entire universe in the laws of Newton, that Newton and Leibniz who has framed, and we were going quite right in predicting the laws of nature and the exact behavior of the system. Enter Albert Einstein. Revolutionize the entire way in which you look into space and time. So with a special theory of relativity, we got the relativistic effects. So the entire principles of Newtonian mechanics got changed into special relativity. Force became force, momentum became momentum. All those things really changed, and we got a lot of new things like length contraction, proper dialectics. Then came the master blow, that is Einstein's General Theory of Relativity, published in 1915, entirely revolutionized the way in which we look into the world. The gravity, which was considered to be a fictitious force by Isaac Newton, was now being replaced by what is called a space-time curvature. The curvature is something which causes gravity. It is the dent, it is the movement of the matter in space-time which causes gravity. We got the advent of tensor analysis and a lot of new theories. Non-Euclidean geometry got revolutionized into non-Euclidean geometry, and we got space-time manifold, and we all know how things really changed with the advent of general relativity. With the advent of general relativity, we also understood what is a redshift, how the starlight deflects due to presence of mass, and the extreme conditions we try to find out, black holes and wormholes. Now the problem was that, as I was telling, that when we are trying to predict the behavior of black hole, when things are into singularity, when things are pointed out into a very infinitesimal small dense point, then quantum fluctuations become very important. Quantum fluctuations or quantum field theory becomes really important, and during this time the attempt to reconcile everything is basically came into play. However, quantum mechanics has its own nature, which is called the probabilistic nature. Now, in quantum theories, these physical quantities, for example, position, momentum, they really don't have any value. They really don't have any value in the sense that we cannot position or find out an electron at a specific point. We only can tell that there is a probability of finding the electron, photon, or any subatomic particle in a particular place. That means we are dealing with probability, not with definite measures. So gone are the days of classical, general, or Newtonian mechanics. Now we can only tell that a particle might or might not behave, that there is a probability of behavior, and that is called the probability density. So the conceptual difficulties which arose reconciling quantum mechanics and general relativity was the nature of the gravitational interaction, in particular the equivalence of the gravitational and inertial mass, which allows one to represent gravity as a property of space-time itself rather than a field which is propagating through space-time in the background. This is the basic point which you need to understand also, that the nature of the gravitational interaction, in particular the equivalence of the gravitational inertial mass, is allowed to represent as a nature of space-time itself. That means the space-time's itself nature would allow to define gravitational inertial mass, whereas quantum field or quantum field theory is more represented as a field propagating through space-time, and one is, as we more attempt to quantize gravity, one is subjecting some of the properties of space-time to quantum fluctuations. So this is the difference, that this is considered to be a nature of space-time, whereas in quantum mechanics it is basically a field which is propagating through. So the curvature of space-time, or Einstein's general theory of relativity, which is considered to be a behavior of space-time, when we are trying to quantize or trying to measure in terms of quantum theory, there are two problems. The first is that we are unable to define, because that is a very much classical deterministic system. This is a probabilistic system. Point number one, we can find out things over there through, given the initial position, we can only find the probability density and the probabilistic nature where that subatomic particle would be. That is more or less a property of space-time, point number two, and this is a field which is propagating through the system. That is why we need what is called a quantum gravity. And now here comes another genius, Werner Heisenberg. Right on the screen, you already know that Heisenberg's uncertainty principle, the more certain we are about where the electron is, the less certain we are about where it is going. The more certain you are about where the electron is going, the less certain is about where it is. So there is a problem. The more precisely we are trying to measure one particular position, we are losing the another value, and vice versa. So right on the screen, I have just given a screenshot of the physical quantities are described by quantum state, which gives probability distributions. If you try to measure one property, giving rise to decreased specificity of conjugate property, this is an expression of Heisenberg's uncertainty principle. So I hope till now you have got the central idea that when we are trying to define a classically deterministic system to a probabilistic system, there lies a problem. Also, the space-time itself is the nature of geometry. I mean to say, it is the nature of the system itself. Here we have to define in terms of field that is propagating. We can define there which is a position, momentum, velocity, everything. Here we can only say that this is only just a probability. So this is basically the need of quantum theory of gravity, or which we call popularly as quantum gravity. So the uncertainty principle or the deterministic system needs to be reconciled with the quantum gravity. Is that possible? Let us find it out in the next part of our video. Okay, so here we get a step back and we try to find out what is called a perturbation theory, or what we call is a perturbative re-normalization. Now, see, perturbation is something, wiggling around things. So, in general, we can just tell a perturbative theory is a kind of a theory where we cannot find the definite value of a system. Given any kind of a calculation, we can only find the probability of the answer. Maybe the answer is probable 70% or 80% or something like that. It's a very gross and a very generic definition of probability theory, but it carries more. So quantum mechanics actually use a perturbative theory. So let us take a quick look on what is a perturbative theory. So in mathematics, perturbative theory comprises for finding an approximate solution to a problem by starting from the exact solution by a related or simpler problem. So you see that quantum mechanics, because of its probabilistic nature, uses perturbative theory. So perturbative theory is something where we can get an approximate kind of a solution, and because there is a perturbation going on the field, so QFT or quantum mechanics uses perturbative theory. So far so good. The next question is that in order to measure those perturbative theory, we have a system which is called re-normalization. Right on the screen, I have given a very clean and a very small definition of re-normalization. It is the procedure of quantum field theory by which divergent parts of calculation leading to nonsensical infinite results are absorbed by redefinition into a few measurable quantities, leading to a finite answer. This is important. So when we go into quantum mechanics, you will see that a photon gets split up into electron and then into positron and then to many subatomic particles, which yields to infinite amount of quantities and which would require infinite experimentation in order to get hold of that result. So a particular particle, when it is splitting up to many other particles, then we have to do the measurement which becomes infinite, and it is not possible humanly to find out the infinite experiments. So physicists have designed a formula or a system which is called re-normalization, where we are cutting out those infinite possibilities and we are defining something in terms of finite definite calculations. Now this is what is called re-normalization. So perturbative theory is something which is related to QM, quantum mechanics. When there is a perturbation, we can only find out a probabilistic result, and because these perturbation creates infinite results, we do the re-normalization. But the problem is something different. The problem is that when we try to use those re-normalization techniques, that means we are discarding the infinite possibilities and we will only take the finite definite results. Gravity shows that this is something which cannot be done. Gravity is perturbatively non-renormalizable. Okay, it is a wrong English, but physicists never care about English. So it is called gravity is non-perturbatively non-renormalizable. So what I'm trying to tell is that in the classical definition, if you consider Einstein's general theory of relativity as a very classical definition, then what you will see is that using Einstein's field equation, the general G mu nu, which is the metric tensor, and where we define metric tensor in terms of the causal structure of space-time, and then we use T mu nu, which is the stress energy momentum tensor, which defines that how matter behaves around the space. And when we try to renormalize these things, it results into infinities. Okay, so there are two ways in which we can renormalize gravity. One is using Feynman diagram. I'm not going into the mathematical details, right? Because it would take again a separate video to show you. It's quite simple, but anyway, we can show how Feynman's diagram actually results into ending up infinite number of couplings. We know what a coupling constant, so we use the same coupling constant by using Feynman diagram, using gravity, and we get infinite number of couplings, which makes it non-renormalizable. Second thing which requires is that the mass dimension of Newton's constant, which is G equals to 2 minus D, which also yields to what we call non-renormalization. That means if we take gravity and we put it into several dimensions, again I'm not going into the mathematics, then it would result into something which is 2 minus D, which actually shows, that means the value of d would result into minus if it is greater than 2. Value of d would be negative, it results more than 2. So this again goes into what is called non-renormalization. So gravity is basically finite number of couplings. So herein starts the basic challenge of us, that how we have already normalized those infinities in quantum mechanics using the different fields, but we are unable to normalize gravity, because every time we do, we get a infinite coupling, we get infinite values, and more importantly the Newton's, I would say Newton's constant is yield to something which is non-renormalizable. That is why I told right at the beginning that gravity is perturbatively non-renormalizable. Now the question arises, if gravity is non-renormalizable and quantum mechanics is normalized, and is there any way then we can reconcile that? That will be expressed when we take a note of what is called the 4 fundamental forces of nature. So the 4 fundamental forces of nature are basically, we know, are called fundamental because we cannot further divide and get into sub forces or something. Right on the screen is a schematic diagram. So the 4 fundamental interactions, also known as fundamental forces and interactions, that do not appear to be reducible to more basic interactions. So the gravitational and electromagnetic interaction, which produces significantly long range forces, which affects can be seen in everyday life, and the strong and weak interactions which produce forces at minuscule subatomic distances and govern nuclear reactions. So each of the known fundamental forces can be mathematically described as a field. The gravitational force is obviously given to the curvature of space-time, which is described in Einstein's general theory of relativity. The other 3 discrete quantum fields and their interactions are mediated by elementary particles, which are expressed in what we call is a standard model of particle physics. So we know already now that there are 4 fundamental forces: the gravity, which is big in nature but tentatively weak; electromagnetism, strong and weak forces. All these rest of the 3, electromagnetism, strong and weak, has been categorized under and normalized and put under the elementary particles of standard model of particle physics. But the problem is with gravity. The question now rises is that what actually guides those fundamental forces? We understand there are fundamental forces, but there should be some kind of a force which guides them. Let us quickly find out in the next part of our video. Okay, so the force carrier are called also gauge bosons. So right in the screen I have given with the standard model, the strong interaction carried by a particle is called gluon, which is responsible for quarks bonding together. The weak interaction is carried by W and Z bosons, which is also acts as nucleus of atoms mediating radioactive decay. And the electromagnetic force carried by photon creates electric and magnetic fields which are responsible for the interaction. I have mentioned that gravity also must have a force in order to define. That is what is called gravitons, which are a theoretical particle. We have not yet found it out. So these 3 particles, strong, weak and electromagnetic force, are being carried out by another gauge boson, which is the carrier. That means it is carrying those forces: gluons for strong force, WZ bosons for weak force, and photons for electromagnetic force. To match with the theory, we need to find out another force which is a carrier for gravity, which is called gravitons. Now the question rises that if gravitons mediate the gravity, then gravity causes space-time curvature, right? We have seen that in Einstein's field equation. Question to the physicist rises that, is that space-time curvature, I mean to say, which causes the curvature, also will affect the subatomic realm? I mean to say, if gravity or mass causes space-time curvature, then electron, positron, all the subatomic particles, although they have negligible mass, must cause a wrapping around the space-time, isn't it? Although it is very minuscule, it doesn't make any sense, but theoretically or even mathematically, the presence of mass should cause a wrapping around the space-time curvature, right? So is it that the curvature around the electron is also curved? Let us find it out, what we are trying to mean in the next part of our video. So as you see right in the screen that I have shown you the Einstein's field equation. So the left side, because it measures curvature of space-time, and the right side presents matter, the effect of gravity and the curvature of space are relatively obvious at a more zoomed out curvature around particles grows fatal in various situations where lots of mass and energy is twisted around an infinitesimal point, right? And that is what is black holes, and it is in an infinite point where at Planck's length we are trying to find out the curvature of space-time. So even if it is minute, mathematically there should be a wrapping of space or time or space-time around the electron. Now in order to define that, I mean to say the space-time curvature, either it can be at the Planck's level or we are trying to reconcile quantum mechanics with gravity. There are two thoughts which arose. The first one is designed by the famous physicist John Wheeler, and what it is called, let us find it out in the next part of our video. This is again theoretical, coined by the famous physicist John Wheeler, which is called a quantum foam. Okay, it's kind of a, you can just visualize what is a quantum foam. I will just show you. Find out the definition. Quantum foam is a theoretical quantum fluctuation of space-time on very small scales due to quantum mechanics. So when there is an incomplete quantum gravity, it is impossible to be certain what space-time looks like in small scales. However, there is no definitive reason that space-time needs to be fundamentally smooth. It is also possible that it can be bumpy. So Wheeler suggested that the uncertainty principle might imply that over sufficiently very small distances and sufficiently brief intervals of times, the very geometry of space-time. School of thought, especially John Wheeler and others, hypothesized something which is called a quantum foam. That is, there is a perturbation, and as it has been denoted that the very geometry of space-time fluctuates. These fluctuations could be large enough to cause significant departures from the smooth space-time which is seen at a macroscopic level to something which is a foamy character. This is one school of thought which is trying to, again define the space-time curvature in quantum realm using what is called a foam. This is called a quantum foam, and the quantum foam is actually that the space-time is not smooth as per general relativity, but it is something bumpy, and here the quantum fluctuation takes place. The next school of thought find out something very interesting. So what is a graviton? Let us find it out with a quick definition. In theories of quantum gravity, the graviton is basically a hypothetical quantum of gravity, an elementary particle that mediates the force of gravitational interaction. As you see on the screen is a hypothetical quantum of gravity, an elementary particle that mediates the force of gravitational interaction. That means as per the standard model, the one part which was missing, that is the graviton, so we just substituted one small particle so that it also acts as a mediating force, and as the other mediating force, photons, WZ bosons, the same thing or the same nature it would be. So gravitons have got some special characteristics, although it is not found, it is hypothesized to be so. A spin 2 boson. Now there is a reason that it should be a spin 2 boson, because massless, because give rise to force indistinguishable from gravitation, because massless spin 2 field would couple with the stress tensor in the same way that gravitational interactions do. Right, so this is hypothesized to be a graviton which is not yet visible in LIGO or any other what we call particle accelerator labs, but we are trying to find out, the physicists are trying to find out something which is called a graviton. Why? Because gravitons will be spin, will have massless, will be spin 2 because it will couple with the stress energy momentum tensor, all those calculations. So till now we have found out in this video that what is the problem of reconciling, quantum mechanics. One field of thought is quantum foam, the second is graviton, and if graviton is found as a mediating particle, then the entire thing matches and we are able to find out the theory of everything. We are able to find out, I think, the entire problem of physics will be solved. However, this quantum gravity has got several other I would say school of thoughts. Let us say school of thoughts are several other theories which supports in either way but in different parameters. Let us find out a little quick glimpse on what are those theories all about. These are called candidate theories. That means these are supporting which are coming up in quantum gravity. The first and the most popular, and Professor Leonard Susskind is considered to be father of string theory, is number one, string theory. So in physics, string theory, what comes is a theoretical framework in which the point-like particles of particle physics are replaced by a one-dimensional string, just like a thread, right? String theory describes how these strings propagate through space and interact with each other. On distances larger than the string scale, a string looks just like an ordinary particle with its mass, charge and other properties determined by the vibrational state of the string. In string theory, one of many vibrational states of string correspond to one graviton, a quantum mechanical particle that we know carries the gravitational force. So this is one very upcoming and demanding theory, which is string theory. The next one is called loop quantum gravity. Just a quick glimpse of what it is. So loop quantum gravity is a theory of quantum gravity which aims to merge quantum mechanics and general relativity, incorporating matter of the standard model into the framework established for the pure quantum gravity case. It is an attempt to develop a quantum theory of gravity based directly on Einstein's geometric formulation rather than the treatment of gravity as a force. As a theory, loop quantum gravity postulates that the structure of space and time is composed of finite loops woven into an extremely fine fabric or network. Another theory which is called asymptotic safety in quantum gravity. So asymptotic safety looks to solve the fundamental problem that is related to these. You don't need some small couplings. I hope you remember that when we are trying to normalize gravity, it leads to infinite coupling, so we don't need that. So rather the couplings to simply be finite in the high energy limit. All couplings constant change with energy. So what asymptotic safety does is that it picks high energy fixed point for and then everything else can be calculated in low energies. It aims at finding consistent and predictive quantum theory of the gravitational field. So there are numerous others: asymptotic safety, loop quantum gravity, which tries to merge general relativity. Asymptotic safety discards the infinite constant, and string theory is the most popular till now, where it describes in dimensional objects, I would say one-dimensional objects called strings. If you're really interested to find out further on what are the other theories, quickly have a look. Euclidean quantum gravity integral method, causal dynamical triangulation, causal fermion system, causal dynamical triangulation, causal set theory, group field theory, and a lot. These are basically candidate theories. Physicists are thinking and evolving. The basic objective is the same: unify quantum mechanics and Einstein's general theory of relativity. All for today's video. I haven't got into the mathematical details, which I will make it up in the next part of the video. So just a quick summary that gravity, being the fundamental force, was discovered as early as human civilization. We can predict everything in gravity, or I would say a classical general relativity system. We can predict everything given a finite conditions. When it comes to quantum theory, we are trying to calculate black hole, or where the general laws of physics or relativity breaks down. We find out something which is called a quantum scale or a Planck scale, where we are trying to define everything with quantum fluctuations. We cannot define general relativity still now with quantum theory. The reasons are: number one, that quantum theory is probabilistic. Classical relativity is deterministic. Number two, the position, momentum, etc. have a definite value. In quantum mechanics, these are all perturbation, or these are probabilities and probability densities. In order to solve that, what we found is that we designed something which is called re-normalization, where the infinities are discarded, but the problem still persists that when you're using gravity to re-normalize, it becomes non-renormalizable perturbative theory. For that, we develop one which is called a quantum foam, where the background is considered as something which is not continuous but which is bumpy. And the next is a hypothetical particle which is called graviton. Possibly if we could develop graviton or find it out, then it would be a massless spin-2 boson which would match with the stress energy momentum tensor and find a safe and happy place in the standard field, standard model. The other gauge bosons were fine with quantum field theory but not with what is called gravitons. The theories which are now still being developed with gravity are string theory, asymptotic, asymptotic safety in quantum gravity, as well as loop quantum gravity and many other things. String theory being the, I would say not popular, being the strongest. We are still in the way to find it out. Thank you very much for watching this video on quantum gravity. My name is Shaunak and I'm signing off for today and waiting to hear from you that shall I make further videos on quantum gravity? What is your feedback? The aim would be the same. Can we find out a theory which marries all the theory? Can we find out something which will unite quantum mechanics and general theory relativity? Does not play dice at one point of time is being done, and we finally find out one theory which merges everything together. Thank you very much for watching this video.
Now, you can be a part of our team. You can send your scientific articles, essays, research papers, lesson plans on a particular subject of science. For further details, please write to us at editor@physicsforstudents.com. Stay safe and happy.